Okay, let's begin. I don't know, but I got the impression that you guys had trouble with that quiz. Am I right? Let's actually quickly go over it. The solutions are already on the website, but I guess I just want to talk through it with you guys. Yeah, which of the properties were not a property of a vector field? A vector space. Right, so that was U. I'm doing version A here. Version B is similar. I gave you that property. I gave you this property. I gave you this property. I gave you this property. Every U has a negative was another property. And if U is in the vector space and is non-zero, then there exists a multiplicative inverse. Okay, which ones were not properties of vector fields? The second one? And the last one. What made you figure that out?
Never saw the second one.
I didn't see the list. That's actually a good way to do it. What's another way that, let's say you forgot the list? What was our intuition here?
When we talk about vector space, we don't mean only numbers, but we mean different things.
Yeah, like what kind of things?
Like matrices.
Scale.
Matrices are one of them. Would this be true for a set of matrices?
No.
No. So it can't be a property of a vector space. Another thing we realize from vector space, remember there were two operations that were defined for vector spaces. What were they?
Addition.
Addition between
Vector.
vectors. So I know I can add two vectors in a vector space. What was the other operation? Scalar multiplication. The multiplication that's defined on a vector space is multiplication of a scalar with a vector. Here I'm telling you multiplication of two vectors. This wasn't even a defined operation for a vector space. Right? It's definitely not a property. Which again would tell you that this one does make sense because that's multiplication. We also know that inverses don't always exist for all non-zero numbers. Again, matrices would be an example. Not every matrix has an inverse. Right? So these two are not the properties of vector spaces. Okay. In 2, I actually gave you a couple sets with operations and I wanted you to find out whether they were vector spaces. Right? So I said X is the set of all vectors of the form X0. Of course, X is a real number. Standard operations on R. We are in R2. Standard operations on R2. Right? Of course, the standard operations just mean if I add two vectors, then the result is just adding the components. That's the standard operation for addition. And then scalar multiplication, if I take the scalar multiple of a vector, it's just I take the scalar multiple of each component, right? So when I say the standard operations, these are the two I'm talking about. Okay, so with those two operations, is the set of all vectors that have 0 in the second coordinate, do they form a vector space?
Yes.
Yeah. Yes, it was a vector space. Right? And you can check the list. You'd realize if you try to think of one that won't work for this example, you couldn't find it. The second one, though, was this also a vector space? Set of all x, y such that x is greater than 0. Right, so this is a subset of R2. Standard operations again. did this form a vector space? Why not?
You cannot find a vector in that, and if you add them, you cannot find 0 because it's all positive.
Right. No. One, you can say no negatives is a problem. Right? If your x is strictly greater than 0, there is no vector AB such that if I take AB and I add it to xy, I would get the 0 vector. It would be impossible, right? Because in order for that to give me 0, I need this guy to be a negative of that guy, which means it violates this form, which means it's not in the space, right? And another reason, and again another reason why you can say that you can, if you give me any one reason, I'll mark it correct. Another reason would be not close under scalar multiplication. Right? But since if my k is actually negative, then k times a vector would not be in the set. Because then that would make my first coordinate negative, potentially. Right? So it's not closed under scalar multiplication, and we don't have negatives. There are vectors where I cannot get to 0 by adding to another vector. That's bad. I need that in a vector space.
I have a question before you erase the second part. When we began this, the chapter, we had an example where we had, but it was u and v, but we had the second part equal to 0, but we found that it was not a vector space. I don't know how this differ to that example.
Was that the scalar multiplication operation?
I can read the example where we have w equal to r squared such that u and v is element of w.
Okay, so here's a side note. Previous example. Right, so how do we define these?
Define w equal to r squared such that u, the vector u and v are element of w. K is an element of r. Then u and v are equal to the sum. But later you ask the question, what about u plus v equal to u plus v, u1 plus v1.
How did I define that?
U plus v equal to u1 plus v1 equal to 0.
And this is 0?
Yeah, 0.
Okay, so I'm saying that u is u1 comma u2, and then this was v1 comma v2.
Yeah.
And then I said I defined addition that way.
Yeah.
And what did I say about scalar multiplication?
Scalar multiplication. You went quick on it, but the conclusion was it was not a vector space. I don't know if I, wrong.
Right, so this I defined normally, well, typically, with the standard operation, right? But here I changed addition, right? I changed an operation on the vector space. Right, here I'm using standard operations, right? Addition was normal. But here, I actually changed what it means to add two things, right?
Okay.
And I didn't restrict what numbers I could put here. V1 and V2 could be anything. It's a very different situation from this. Here I'm saying the only vectors I'm even considering are the ones where the second coordinate is 0, right? Whereas here, I could consider any two things. I just changed the way in which I decided to add them, right? To get this as the result, right? My result will always look like this, was the question, right? So in this one, I actually changed what it means to add, right? That's why it was different. I actually changed what plus means on all of R2, right? Where here, I'm not even looking at all of R2. I'm only looking at guys where my y coordinate is 0. And I didn't change what addition means. right? My addition is the normal guy, right? It's actually two very different situations.
Okay.
So yeah, you have to be careful. What was the next one? Okay, so I know in part 3, U was a subset of V. What are the two things that I need for U to have, two properties to make it a subspace?
Connection. Please
It has to
connect
be
and
closed
try
under
again.
closure on the scale addition.
Right. Closure under addition is one thing I needed. Right? You could write that phrase and I'd give you the point. Another point is you just want to say, you could write it more mathy looking, right? You can say if U1, U2 are elements of U, then the sum is an element of U. You could say that, and it's the same thing, right? Or you can write closure under addition, and I'll assume you know what that means. Some people remember the phrase, hopefully you remember what it means. I'll give you the benefit of the doubt this time.
Thank you.
Because,
Thank you.
right, but in a test, if you actually don't know what it means, it will come back to bite you. Right, the second one was closure under scalar multiplication. Or to say that in a more mathy way, you can say if K is in my field and U is in U, then K times U would be in U. Right? Once these two properties are fulfilled, any subset of our vector space will itself be a vector space, and we call it a subspace. We just need to check these two conditions, and that's it. Which segues nicely to question 4, where I asked you about the solution set to a matrix equation. And I asked you to prove that the solution set is actually a subspace, meaning these are the two things you need to check. Right, so I said, okay, we're considering AX equals 0 vector. Right, my X and my 0 are elements of some vector space V. W equals solution set to this guy. Right? Of course, you should note that the solution set is actually a subset of V. And I want you to prove W is actually a subspace. Meaning, the solution set to a homogeneous equation is actually a vector space. Right? And later on, we're going to even call this the solution space because of that. Right? This is a subspace of V. Right? So, what was the first thing we had to do?
Closure under addition.
Closure under addition. So we have to prove that we need to show. You don't have to write this. I'm just writing it down for your benefit. We need to show that if x1 and x2 are both elements of the solution space, then their sum are elements of the solution space. Right? That's what we need to show, right? So then we assume x1 and x2 are there. What can I say about the sum? How do I figure out if the sum is there or not?
X1 is 0, X2 is 0.
Right. This means that AX1 would give me the 0 vector because it's in the solution space to this equation. And AX2 would give me the 0 vector because it's in the solution space to that equation. So what can I say about the sum? Is it in the solution space to that equation?
Yeah.
Well, if I plug in the sum, the properties of matrices says this matrix can actually distribute 1, x2, which is 0. This is going to give me a 0. That's going to give me a 0. 0 plus 0 gives me 0. So the sum is in the vector space. The sum is in the solution set. Right? If I know two individuals solve this equation, it turns out that by adding them, the sum will also solve the equation, which means the sum is in the solution set. So it's closed under addition. Now I have to show closure under scalar multiplication. So we need to show. And this is sort of one instance where you would need to know this is what it means to be closed under addition, right? So if you wrote that sentence down, you didn't really know what it means, you'll get stuck on the next problem. So what do we need to show here?
AKX.
Right, well if k is in our field and x1 is in our solution set, then what must be true?
AKX. One.
No, like what I want to prove in general first.
KX1 is in.
I want to prove that kx1 is in W. Right? So ultimately I'm just writing down what I want to get to, right? So then if I assume x1 is in W, then if I take a times a scalar times this guy, what is that?
AK times.
We can factor scalars out. That is a property of a vector space. And this I know is 0, k times 0. But we've proven in a theorem that a scalar times a 0 vector gives us the 0 vector. Not an obvious fact, by the way, even though it feels that way. But remember, we're not thinking Rn. Things can be a lot more general. We actually had to prove this in a theorem, and so this means k times x1 was in W.
Doesn't have to be k to the n ax1 because ax is not a vector space. X is vector space there.
A is a matrix.
Yeah, so that's why it has to be k to the n, I guess.
No, I wasn't multiplying A by k. I'm multiplying the x by k. It's different.
X by k.
It's the x that was being multiplied by k, not the A.
Yeah, but can you write like that? That's matrix. Can you write it that way? I think that's k to the n because you can write ak parenthesis x1 is 0.
Yeah.
AK is a matrix, so you multiply a with k. It has to be k to the n a. No?
No?
Yeah, no.
No,
I
that's
made a
not true.
mistake.
Yeah, that's a mistake.
Yeah.
I think you're thinking determinants, maybe.
Yeah, if you take some.
Yeah, the determinant of k times a
Yeah.
is k to the n a. Yeah,
Yeah.
times the determinant of a. Yeah, but no, with the scalar, you just
Yeah.
factor it out. But that's it. So anytime, which means kx1 is in W. So yeah, anytime you want to prove something is a subspace, you just have to prove two things. Prove that if you add two things that are in the space, you get something that is in the space. And if you take a scalar multiple of something in the space, you also get something in the space. Right? And a lot of the times, to figure out if something is within the space, you're just checking does it fulfill some property that I want, right? So here, to be in W means you need to solve this equation, right? So if I want to see if the sum is in the vector space, I need to check, does the sum solve the equation? If I want to check if the scalar multiplication is in the vector space, I have to check, does that solve the equation, right? Because being in W means solving that equation, right? So a lot of times you'll be able to tell what you need to prove. You know that I'm looking for a set that does a certain thing. And then I want to prove it's a subset of something else. I need to prove that the sum of things does that, and the scalar product of things does that. So, well, this is kind of going into what I wanted to do today. So, but do I still give it? We'll probably repeat this. But what does it mean to be a span? This is the bonus. So W is equal to a set of vectors, W1 all the way up to WR. So to say that W spans the vector space B.
Wouldn't it be that W has to be in the set of all the linear combinations in U? Or
No, it involves linear combinations, but that's not necessarily really the relationship.
The linear combination of W has to be subset of V.
It's stronger than that. It's stronger than that.
Subspace. No.
This means every, and I do mean every, vector in V is a linear combination of vectors in W. Right? Meaning I can write V for any guy I pick here, any random guy at all. I can write him as C1 times W1 plus C2 times W2 plus blah, 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 all the way down to CR times WR. Right? If I can do that for anyone here, I can say this guy spans that set. And I gave an example last time, like I and J spans R2. Right? That was the example. Right? Any vectors in R2, I can write them in terms of I and J. I can write any vector here as a constant times I plus a constant times J. Right? So when in linear algebra terms, that says the set IJ spans R2. Right? That's how we phrase that. Right? In fact, I and J go even further. They don't just span R2. They actually form a basis for R2. So when we said that W is a basis for V, what did that mean?
It means it's linear independent and you have to span.
Right. Two things. W spans V and is a linearly independent set. Now, I didn't really just define what these things meant, but it's a bonus problem. So we are going to define them pretty soon. But that's what it means. And I want to tell you the definition. Well, we'll go over. I'll probably re-explain why this is true. Linear independent means the only solution to C1W1 plus all the way down to CRWR equals the zero vector is the trivial solution for the constants. Right. If you can set up a linear combination equal the zero vector, and the only way to solve that equation is to make all the coefficients equal 0, we say that it's linearly independent. Right? Now, I'll go into conceptually what this means when we get to linear independence, but that's what it meant. So if this is true, and at the same time this is true for the same set W, we say W is a basis for V. And in fact, IJ, the set IJ is a basis for R2. Because IJ spans R2, since if AB is in R2, then I can actually write AB as a linear combination of I and J. And IJ is a linearly independent set. Since if I set up this equation C1I plus C2J equals the zero vector, that would mean C1 comma 0 plus 0 comma C2 equals 0 comma 0, right? So that actually for C1 must be equal to C2 must be equal to 0. So they span R2 and they're linearly independent. Therefore they form what we call a basis. What about dimension?
It's the number of bases.
It's the number of basis vectors. Right, so exactly. So in part C of the bonus, I asked you, if I know that W is a basis for V, what is the dimension of V? Was the question. Right? It turns out it's the number of basis vectors. The dimension of a space equals the number of basis vectors. And so in this case, the number of vectors in my set was R. So R was the dimension of V. So the bonus actually brought us all the way up to, I think it's like 4.5 before we see this. But these were in the very next section. And we'll be talking more about this and what it means. But that was the bonus. I think I was going to do, well, I'm going to expand more on this. Yeah. So these are bonuses. We didn't get them. That's fine. We'll actually talk about them now. But the previous ones there are some very important ideas there that you need to make sure you get. Right. So things. Why do we know that R2 has 2 dimensions? Well, there are 2 basis vectors. And probably what we'll be able to show by the end of today is that the basis that you choose for a set is not unique. There are actually more than one ways to find a basis set. But you'll always have the same number of vectors to form a basis for a given space. Right? The dimension is not going to change based on the basis, but there are many different bases. Okay. Let's move on. We are still in section 4.2. So this is the section on subspaces. So here I'm going to talk about span. So is everyone's phone going on? What is it? W be the set of all linear combinations of vectors in S, and then W is a subspace of them. And W equals what we call the span of W1, W2, W1. Or the span of S. Right, so the span of a set is the set of all linear combinations of vectors in the set. We can also say W spans S and call S just introducing some terminology here. So I'm defining what span kind of means. Right, span just means it's the set of all linear combinations. By the way, span, note, span of S just equals the set of all possible linear combinations. C1W1 plus CRWR such that the C1s are elements of our field and the W's are elements of S. Right, it's just the set of all possible linear combinations. We don't only talk about Rn, but a lot of times we will be talking about Rn, so there's some terminology we need for Rn. These are called the standard basis vectors. Denote them by e's and subscripts. So E1 would be 1 with everywhere else 0. E2 would be 1 in the second place and 0 everywhere else. E3, 1 in the third place, 0 everywhere else, etc. So for R2, you're kind of used to these guys right now. E1 is equal to 1, 0, which we call the vector I. E2 is equal to 0, 1, which we call the vector J. For 3, E1 would be 1, 0, 0, which again we call the vector I. E2 would be 0, 1, 0, which we call the vector J. E3 would be 0, 0, 1, which we call the vector K. Right? So for something like R4, our basis vectors are E1, E2, E3, E4, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. 0, 0, 0, 1. The set. Let's start over here. The set E1 all the way up to En spans Rn. i.e. every vector in Rn. Can be written as a linear combination vectors in the set E1 all the way up to En. I.e. So I'm writing all the ways we can express this in Rn, and a very similar concept can be applied to other vector spaces. I.e. If x is an element of Rn, we can write x equals C1 times E1 plus C2 times E2 plus Cn times E1. Or C1 are real numbers. Another important example about span, to show that they don't have to look like this, they don't have to look like vectors in the conventional sense. Set of all polynomials is going to be another common example we're talking about. Set of all polynomials of degree n or less. It turns out the spanning set, the standard, the standard basis for this guy, for Pn, i.e. the linearly independent spanning set is the set 1 x squared all the way up to xn. Right? So these guys here are vectors. Right? So we don't think of the vectors as something with coordinates. It could be a power of x I could think of as a vector. Powers of x follows all the 10 rules that we had in the beginning of 4.1. If I add them as I did with polynomials, they will actually fulfill all 10 conditions, right? So we know that the set of all polynomials of degree n or less actually forms a vector space where our vectors are powers of x. X to the 0, x to the 1, x to the 2, all the way up to x to the n. Right? Because any polynomial in Pn can be written as a linear combination of these guys. You can write any polynomial to look like that. Let's do an example. To test our knowledge of spanning, determine if the following sets span so get the span of R3. A. Give you this set of vectors, 1, 2, 1. 0, 1, 1, minus 1, 0, 1. And B. 1 minus 1 minus 2. 2, 1, 1. 0, 0, 1. Right. So I just gave you a random set of 3 vectors. Do they span R3? Like I can throw in a third example. C. How are we going to determine this? What must we check? It could be a random set of vectors, asking if it spans a space. What are you going to try to check?
Linear independence.
No, spanning has nothing to do with linear independence.
You can express as linear combination.
Linear combination. I need to show, can any vector in R3 be expressed as a linear combination of these vectors? So what I'm going to do is, I'm going to take a random vector in R3. Let A, B, C be a member of R3. Need to check if there exists say C1, C2, C3, such that if I take C1 times the first guy plus C2 times the second guy plus C3 times the third guy, can I end up getting ABC for some constants C1, C2, and C3? Right? I'm not sure if this is true. So basically, if I want to know if something spans a set, I need to set up a linear combination equal to any random element in that set and see, does this equation have a solution for these coefficients? So does it? How do we go from there? Right, I can combine one side into all these vectors, right? Into one big vector, because you have the standard operations. Right, so I would have, in the first coordinates, I would have 1C1, no C2, minus C3. That's my first coordinate. Second coordinate, 2C1, plus C2, no C3. That's my second coordinate. Third coordinate, C1, plus C2 plus C3, right? So now I want to check, does this have a solution in the C's? Well, what can I do now? If I want to solve that for the C's, how would I do that? C1 minus C3 must be equal to A. 2C1 plus C2 must be equal to B. C1 plus C2 plus C3 must be equal to C, kind of in the system of equations. And we actually know how to deal with these. Finally something familiar, right? So in actually trying to find whether these guys span a set, I end up with a system of equations. And now what I can do is I can actually write this as a matrix equation if I wanted to. I can say 1, 0, minus 1, 2, 1, 0, 1, 1, 1, and set that equal to A, B, C. And I can actually solve to see if there are solutions for C1, C2, and C3 that will give me that A, B, C. Right? Another way. And we can solve this. We can try to solve this. if there is a solution, then yes, the set spans R3. If the system is inconsistent, then it doesn't span R3. One option is the following. Let A be the coefficient matrix. Then what you can do is you can actually find the determinant of A. And if determinant of A is non-zero, what does that mean?
There's a unique solution.
There is a unique solution. So we can get that from like Kramer's rule or something similar. In this case, here, I think I actually computed the determinant before. Here, our determinant was actually 0. So we can't get away with that. But it's always an option, just so you know. So what we'd have to do here, do the row echelon form, and hopefully you get something that's consistent. But what would that mean here? If the determinant is non-zero, what does that mean?
There is non-zero.
Yeah, if the determinant is 0. Yeah, what would that mean? We have a row of zeros somewhere, right? So that means reduce row echelon form. Right? So we're using concepts to get out of work. We want to be lazy, right? Reduce row echelon form is going to be something like this, right? There's going to be a row of zeros here. And what's going to be over here? Well, I'm not sure. It's going to be some function of A, B, and C, right? Not necessarily inconsistent, but what's the problem with this? So if, what happens is, if this function here is not exactly 0 all the time, then what would that mean? A, B, C would have to fulfill a specific condition, right? And once you put a specific condition on the number, on the vector that I can pick, guess what? It won't span, because it means that any vector that doesn't fulfill that condition, I cannot write as a linear combination. So, actually, when you check this one, well, we don't really have any time now. Check this one to see if it spans. Do the rest of the examples. We'll pick up with them next time, and we'll continue. Next class is next Monday, right?
Yeah.
So Wednesday is a Friday schedule, so I won't get to see you guys for a whole other week.
4.1 do next week?
Huh?
4.1 do next week?
4.1 is due. Yeah, just 4.1.
Okay.
We didn't finish 4.2 yet.